So in this question, it's important to remember, well, this is basically the entire unit, but energy is conserved. And what that means is whatever the energy is in the system before is going to be equal to the energy in the system afterwards. So actually, let me write it like this. Is equal to the energy in the system after. So we use arrow sort of to show that we mean after. I'm pretty sure that's how we use it. It's been a while. And so in a question that has an individual standing at the ground here, and so let's say it throws the ball all the way up, and it's asking us to find the height. What that means is that the kinetic energy in which he releases the ball will be equal to the gravitational potential energy all the way up here. So let's look at our givens. And so the only given that we actually have is the velocity of what he throws the ball at, which is 11 meters per second. But that's all we need. In this question, we have the kinetic energy, and we also have the gravitational potential energy. For now, we'll write it like this. And so some important things to know is that in this question, as the ball is flying towards its maximum height, the kinetic energy decreases. Therefore, so we should write it like this: minus half mv squared, and the gravitational potential energy actually increases. So we need to write it like that. So that's what we're going to do. Equals 0. Now, just to simplify things, we'll move all of this to the other side. So mg change in y is equal to 1/2 mv squared. And because there's mass on both sides, let's just cancel those out. So we get 9.8 and 2, and the change in y, which is, if you don't know, we need to find that, half, and then we have 11 squared. So on the right side over here, we should get 60.5 on the left side, 9.8 change in y, delta y. And in the end, divide both sides by 9.8, and you'll find that the ball's maximum height is 6.2 meters once you round to two significant digits. Okay, so that's part A. Part B and C both involve you making a graph. And so the first graph that we're going to make is of time and height. In fact, it's always going to be time and height for both graphs. We're going to draw them on the same axes. And so if we're just looking at the gravitational potential energy, which I'll make in black, what it should look like is a little something like this, sort of like this parabolic pattern. And what it means is that when the height is at 0, that also means that the gravitational potential energy is at its minimum. However, when the height for the gravitational potential energy is the highest it could be, then that energy is the max. And then again, when let's say once the ball falls, it's going to be at minimum again. So that sort of describes the shape. However, if this was to be if this was a if we were drawing the kinetic energy instead, it might look a little something like this. So on the same axis like this, again, this would be its max point, and again, this would also be its max point. However, when the gravitational potential energy is at its greatest, the kinetic energy is at its minimum. So it could be inferred that the gravitational potential energy and the kinetic energy are actually inversely proportional. So if this increases, then that decreases, like that.